So, hello everybody, and welcome to this Science in Dialogue event co-organized by the Spanish Embassy, the Society for Spanish Researchers in Germany, and the Cervantes Institute. Before we begin, I would like to start by thanking, of course, our speaker of the day, Professor Ignacio Cirac, and of course, the ambassador, Mr. Ambassador. Thank you very much for this ongoing cooperation that you have with our society. We value and cherish this cooperation very much. And the floor is yours if you want to make introductory remarks.
Thank you very much, Guillermo, and yeah, I'm very pleased to welcome all of you here today. And of course, I want to start by thanking very especially Professor Dr. Juan Ignacio Cirac for his agreeing to be our guest in this first session of our Science in Dialogue series that we hope will take up and after the summer break will become something normal and that we will all be using quite often, we hope. My gratitude, our gratitude from the embassy goes also to CERFA. We have the president there, Elisa Garcia, but especially today with Guillermo Pérez Hernández for moderating and leading all the session today. As you all know, Professor Cirac is widely acknowledged as one of the brightest minds in scientific research, both in Spain and internationally. And as ambassador of Spain, I like to feel proud of all our scientists and of all our brilliant citizens that we have around the world. You are real ambassadors of Spain, the real ones, the ones that show that we have high quality in Spain, in this case, in research. He has a very international career, and we all know it now, in Europe and in the United States. And this is very important for Spanish scientists today who have an international profile, as I was saying. Today we have many, but to have someone that in 1980 started and took this decision so long ago, it is important. He's a pioneer, and he somehow is one of those that showed the way to others, and it will be good to listen to him today, as I said, because what we from the embassy would like to do, with CERFA we have already spoken several times, but with all the others that might be interested, is to put in value all the important presence of Spanish scientists, Spanish research in Germany, so that we can slowly show our wonderful host country here, Germany, that Spain has a lot more than just football or sun for tourism. That we are strong, that we have this soft power that is so strong when we talk about our scientists here. I don't want to be very long here, but I want to thank you all again, and I look forward for today's discussion. Thank you.
Thank you very much, Mr. Ambassador. Those were very kind words. I'm happy that you consider ourselves so valuable to your goals. So it is my task today to introduce somebody that truly doesn't really need an introduction. I assume to everyone who's here a certain level of familiarity with the figure of Ignacio Cirac as a researcher and as a person in this host country, that I have decided to go a different way for the introduction. It will be very brief, to also put into value why we think this speaker is of particular interest for this community. Before I start sharing my screen, there's a checklist in my mind. I also want to thank Juan Manuel Vilaplana from the embassy and his co-worker Francisco Paniagua for co-organizing this, and all of the people in CERFA. I see Elisa smiling there behind the scenes, making all of this happen. Now I'm going to try to share my screen and give the introduction for the talk of today. So here we go. If you could confirm that you see my screen and my mouse pointer. Thank you, Juan Manuel. So the left part of this slide you already know. This is the reason why we're here. Perhaps I should start by explaining who CERFA is. This little logo from the Apple over here. This cute, let me move. I think I have to move the, just give me a second. Okay. This little logo over here, CERFA is the Society for Spanish Researchers in Germany. It was established in 2013. Actually, it was its first meeting took place in the embassy. Today, we are made up of about 700 members. Most of it are postdoc and students. We have some principal scientists or professors, and we have also people in the industry. We are mostly funded by the Fundación Ramón Areces, who actually funds us through a lot of activities during the year. These are the events that are coming up just this next month of June. So we have a working group, which is called CERFA Cancer, making quite the impact with their seminars. We have some more public science events like Orbita CERFA, coordinated by the Bavarian delegation, talking about vaccines next month. You can also check out all of this list of previous events that we in the society have been doing over the last 6 years. As you see here in the upper menu, so there's also other things that we do apart from having events and celebrating ourselves for it. There's some money that you can apply for if you're a student and you want to travel. There are working groups who actually carry out different cooperation agreements with universities in Spain. And well, today we find ourselves in one of these events, honoring or actually listening to Professor Ignacio Cirac from the Max Planck Institute for Quantum Optics in Garching. Professor Cirac, again, I said, needs almost no introduction. This is just the sheer size of the current group, made up of about 50 people. Half of them are PhD students, half of them are postdocs. Perhaps he can talk about more about this structure later. This is just the impressive list of awards that Professor Cirac has been granted or awarded during these last years. I find it curious that, you know, in 2013, right after he got the prize, the Wolf Prize in Physics, which is somewhat of a prelude to the Nobel Prize, we decided to make him the first honorary member of CERFA. It's actually a decision that was made in the first meeting we ever had as an actually constituted society. So since 2013, he has been on that exclusive list. So we hope to get also a Nobel Prize on that list rather sooner than later. And to walk us a little bit into the mind or the figure, I am quoting Professor Cirac out of a podcast that he gave to the Juan March Foundation in Spain. Professor Cirac is regularly and very often featured in the media. He makes efforts in science outreach and science education beyond his impressive scientific publication record. So he has said that physics works with formulas, and once we have these formulas and we believe them to be true, well, what science allows us to do is to run the movie backwards, and that it allows us, without having been there, to know what happened before us. And then we can extrapolate and think about what happened when the universe began. Now, I promise you today, we're not going to go back to when the universe began, that there's no time for that. But if we start with where we are now, particularly in Germany, these are just two snapshots of you know, Reuters news agency and the website of the Federal Ministry for Science. Germany has granted about 2 billion euros. The last month, it was decided a couple of years ago to invest in quantum computing, particularly to become a player in the world challenge of achieving something that's being called currently quantum supremacy, because we are supposed to be in something like a Wright brothers moment, where the first plane ever took flight, and it was very rudimentary, and it crashed immediately after that, but it ushered in the era of civil and military aviation. Perhaps this is a moment of hype. Professor Cirac can tell us a little bit more after that. Or perhaps we are about to experience something called a quantum winter, where after all of this hype, it turns out that we aren't as close as we think we are to something like these wonderful promises that quantum computers offer us. We're not going back to the origin of the universe, but we're going back 25 years or 26 years. This article in Nature Review Physics is 26. I mean, it was published last year. Trapped ion quantum computing turns 25. And the interesting part, I hope you can see my screen and that this Zoom thing isn't. It's hard to assign the beginning of the field of quantum computing. But when it comes to the first conception of how to actually build a quantum computer, one result stands out. On May 15th, 1995, a paper by Ignacio Cirac and Peter Soller was published in Physical Review Letters. So this is truly a pioneering event where somebody is actually explaining how a given realization of an otherwise theoretical machine can actually be carried out in real life. This is the paper. There's a reason of why I'm showing you this paper. A quantum computer can be implemented with cold ions confined in a linear trap and interacting with laser beams. Already in this first sentence, I think that, and I hope Professor Cirac takes this as a compliment, its simplicity, it's already beautiful, because if you look at other papers in Physical Review Letters and you read the first sentences of those other papers, they tend not to be this simple. And yet, encoded in this very simple sentence, a new era is beginning. And again, this is of course a compliment to Professor Cirac. I believe high school level AP physics students could understand what is being meant with this sentence. And this sentence was so important that less than 1 year later, some other group of researchers around the group in Boulder, in Colorado, they say, following the scheme proposed by Cirac and Soller, and they put the reference number 1. I also think that it's internally for scientists, this is a very cool way of citing a paper, because usually the first reference in a paper is citing a review or citing some established literature so that you can, introduce your work. Hydrogen bonds are very important in nature because, and then and here these guys just go to the point and you say, we just built what these other guys said that could be built 6 months ago. I am emphasizing this because I want to make, or to show you, a little joke about how experimental physicists feel about theoretical physicists, where they just keep saying, you just need to get the protons really close to each other. I told you that like 30 years ago, and it's still not done. And this is, of course, very frustrating because it might occur to some experimental scientists that theoretical physicists offer concepts that are very, very often not really transferable to the lab. So Professor Cirac actually turned this concept around, him and Professor Peter Soller, and he just said, a quantum computer can be implemented with cold ions confined in a linear trap and interacting with laser beams. This actually makes Monroe, Mikhoff, King, and Itano very happy. And they say, okay, give me just 6 months, 8 months tops. And actually for that realization, among others, Wineland in 2012 won the Nobel Prize for Physics. So this is what happens when you have a team of people that think and people that build quantum computers. With this, I finish my introduction. I hope you enjoyed most of the themes floating underneath it, and I give the floor to Professor Cirac.
Well, first of all, thank you very much, Guillermo. That was an incredible introduction. I mean, I think that you have exaggerated a lot the role that we played, and yeah, but it's been really wonderful. I mean, you explained many of the things actually that happen in a way that really well. So now I feel very I mean, humbled to present, to give my presentation. But anyway, so let me start with a big thanks apart from Guillermo. So first of all, to the embassy, and especially to the ambassador who is present here. So I know very well how busy ambassadors are, and so that he spends time to be with us and also to support the scientists. I think that it speaks very much for itself. So thank you very much, Ambassador, and thank you very much for the people from the embassy for the continued support that you have been giving to CERFA. I think that's something very important. Guillermo mentioned it already that, I mean, I know CERFA from the very beginning, so I still remember when they contacted me, one day sent me an email saying, oh, we're thinking about doing something. And I mean, I had some meetings with some other people and it's a great times, and I'm very happy to see how this grew. And so how now it's transforming something really, which is very important for the scientists working in Germany. Okay, so this is why I would also like to thank CERFA, well, first of all, for making me honorary member in 2013, but also for this invitation to be with all of you and share a little bit my experience. So this is not going to be a talk about science or about some quantum computing, even though I mean, I need to do that. So whenever I give a talk, even if it's a more political talk, I have to talk a little bit about science. Otherwise, I think that I'm not doing my job. So anyway, so I want to give a little bit an idea. This is what Guillermo and Elisa proposed when they talked to me, that I should just make a story a bit about what has been my career, and especially devoted to what Guillermo was presented here. So these are intra quantum computing. And I want to say first that I think that you have to see my presentation as a representative of a generation that was previous to most of you, and that changed a lot, because you know that in this, well, for many years in Spain, there was not so much research. And in the 80s, there was a decision taken by, I mean, politicians, society, and whatever, to start thinking about science. So they actually gave us money to go abroad to some of us, and this proved to be very useful, and this was the starting. And so I'm one of them. So we have different people. I mean, you probably know many of the other of my generation. So I was a lucky one. I mean, I was in the right place in the right time, and this explains many of the things that you will hear today. Anyway, so I'll share my screen, and all right, because I have a little presentation. And so I hope that you can see that, right? Okay, very good. Okay, so I don't want to start just with all my life, but just to say that I studied in physics in Madrid, theoretical physics in Madrid, at the University Complutense of Madrid. And I did there my PhD in quantum optics. So that's the theory that studies the microscopic phenomena, and in particular, the interaction of matter with light at this microscopic level. I have to say that at that time, I was not sure about what I wanted to do. I was not sure that I wanted to become a scientist. I was not sure that I wanted to go to continue in the university. I didn't know if I want to do go to the industry, maybe do something else. So actually I was checking many options, but it was when, due to this, I mean, I had one of these grants that they're giving at the ministry that allowed me to go abroad for some time. And there is where I met Peter Zoller, and in during my PhD. And this changed a lot for me, because I saw that there was a different way of doing research, and very motivated. So somehow the research that I was doing at the University Complutense was not very motivated. So I didn't know very well why I was working in what I was working. Whereas when I went to Innsbruck for 3 months, then, I mean, they told me why I was doing that, why they were solving that, well, why this have impact, why this will be significant, why this is a brick in the wall that we're building in physics. And for me, this changed already the perspective. And after that trip, I wanted to become a scientist. And I was extremely lucky. So when I finished my PhD, when I was about to finish my PhD, I had planned to go as a postdoc to the US. Peter Zoller had got a professorship in Boulder, in Colorado, the University of Colorado. But 1 week before defending my PhD, it turned out that there was a position advertised at the new university in Spain, at the University of Castilla-La Mancha, and I applied. It was an associate professorship, so professor titular. And I was lucky enough to get it. So for me, it was completely unexpected that all of a sudden I had some kind of permanent position right after my PhD, and I didn't want to do whether to take the position or not. So I talked to the people from the university, and they were kind enough to let me go to the US. So I said, well, I wanted to go to do research in the US, and I want to go there. And so that's, I will be also happy to be here, but I want to do that. And they allow me to do that. Of course, I had to teach, so I had to spend some time in Castilla-La Mancha, go to the US. And this is why, I mean, during about 4 years, I was going back and forth between Boulder, Castilla-La Mancha, and I also spent some time in Harvard. That's a picture of that time. And okay, so after that time, then there was an opening at the University of Innsbruck, a professorship, and then I applied and I got this position. And this was very good for me because the University of Innsbruck, it's a university where quantum physics was very rooted. In particular, Erwin Schrödinger was spending there some time. And so there was at that time also, apart from Peter Zoller, who came back from the US, there was Anton Zeilinger and some other very famous people working in quantum physics, so kind of a mecca of quantum physics. So I was very lucky to get a position there. I worked there for 5 years. And then after 5 years, then I received a call from the Max Planck Society to become director of the Max Planck Institute, where I'm now. This is an institute in Munich, Institute for Quantum Optics. But let me rewind a little bit and go back to this time that I was in Boulder. And so something that happened when I was there is in the last summer, there was a conference. And this conference is an international conference on atomic physics that it's just moving from one place to another. And that time it happened, that summer, it happened in Boulder. At that time I was working in quantum physics, and I was working in atomic physics, in just trying to see how to observe quantum phenomena, very blue sky research with atoms and ions. And then Arthur Ecker, who is the guy who's in this picture, gave a talk and started talking about something called quantum computer, something I have heard of, but at that time it was completely exotic, if not esoteric. So what he was saying is that if we had a quantum computer, if we had a computer based on the laws of physics, then we could do things that we cannot do with classical computers, and that we will never be able to do with classical computers, not even with supercomputers. So this will open up some possibilities that would be fantastic. He mentioned some of them. However, he said, we have no idea of how to build a quantum computer. Nobody knows how to build it, and we don't even know if it can be built. And Peter Zoller and myself were sitting in the audience. And then remember this moment, we said, okay, so we have to think about that. It's a big challenge. Maybe it's esoteric, but it sounds kind of crazy enough. So let's do that. And so what happened is that at that time I had to go back to Europe, and Peter Zoller had to go to some conference to Napa Valley, that's in California. And then he said, okay, let's do the following. So I'm going to Napa Valley. There was an important conference. There was a Japanese-US conference on laser physics, where there were only 12 invited people who were sitting in a room for 3 days just to decide a little bit about the politics on the laser research between Japan and US. And Peter Zoller said, okay, let me do the following. I'm going there, and I smuggled you in the conference. You will not be able to attend the conference, but I mean, you can work at the hotel and we can talk in the evening. And that's what I did. Actually, they allowed me to enter the conference. So I went there, and there was many famous people there, Stephen Chu, I mean, well, Nobel Prize winners, people who became Nobel Prize winners and previous Nobel Prize winners there. And anyway, so whenever there was the evening, then we were just discussing and trying to find out. And at the end, we came up with some idea of how to do that. And that's the paper that was mentioned there. And in this paper, we showed how, in principle, you could build a quantum computer based on trap ions. So we had, and this is why we say it can be implemented. So it's possible to do that, because we wanted to show that it was possible, at least in principle. I also brought this drawing, original drawing, from the article, because it shows our drawing capabilities at that time. They have not improved that much in the meantime, but you see that that's how the way that we were writing paper at that time. So I have to say that this paper has a funny story. It was rejected in PRL, of course, like every paper. Yes, I mean, the referee report was stating that with this problem, that it's not clear that somebody could build it, what we were proposing. And somehow the other referees believed us, and this is why it was published. It has another anecdote that you see that there is a start here from Peter Zoller. And this start, if you go to the reference, it says that Peter Zoller has a permanent address in the University of Castilla-La Mancha. So I mean, we put the star in the wrong person. Anyway, so what happened is after, I mean, we sent the preprint to Dave Wineland. Dave Wineland, we knew him, he was in Boulder. Actually, we were talking to him some time before about some other problems. And then Dave Wineland started working on that, and very soon had the first demonstration of the basic principle that was behind our proposal. Okay, so what is a quantum computer? Well, a quantum computer is a computer that is based on the laws of quantum physics. These are the laws that rule the microscopic world. That's the rules that follow atoms, electrons, molecules, and so on. So probably most of you are familiar with quantum physics. And what happens is that among these rules, there are some of them that are very special and that we are not used to them. There's something called superposition, another word is entanglement. And by using these extraordinary rules that only occur in the microscopic world, then it turns out that then you can do computations that you cannot do otherwise. So, I mean, just exaggerating a little bit. So it's like if you are used to do computations with an abacus, in which everything is mechanical, and all of a sudden somebody discovers electronics, and then you can use electronics to do computation. So you change the roles, then you have more power. Now we change the roles or the rules, and then we can use quantum physics. And so this means that we can do computations in a completely different way. And this is where you get all this acceleration and the possibility of solving problems that are very hard, if not impossible, with super computers. Okay, so then we worked for many years in the scientific environment at the universities, and then you saw that there were papers about how to scale instead of 2 ions or 2 bits, quantum bits, 2 qubits, to 3, to 4, to 5. And so there was some steadily progress, but things changed. And in 2019, there was this but appeared in the headlines in the newspapers that this Google, and this is the CEO from Google, claimed that they have built the first quantum computer or prototype of quantum computer that could solve a problem better than any supercomputer that we have nowadays. And indeed, that was true. So they, just basically invented a problem that they could solve with this device that had at the time these 53 qubits, that if you would use a classical computer would take years or many years to solve it, and they solved it in a few minutes. Okay, and then automatically then the media was full of speculations and talking about that quantum computers will change our world, that fine banks will use quantum computers, retail industry, automotive industry, every industry will use quantum computers. So there was automatically many expectations brought to the general public, to the companies and so on, which created a hype that we are at the moment living and somehow suffering, as I will, if I have time to explain about why, I will tell you later on. In any case, building a quantum computer is extraordinarily difficult. So what we showed in this paper of 95 was that it was in principle possible, but in practice, it's very difficult. And the reason is because you have to harvest somehow the microscopic world in order to use the properties of the microscopic world, the quantum properties, and they are very elusive. They only appear under very extreme conditions. So they occur whenever you have the vacuum. There is no other particle except the atoms, which are part of your quantum computer. So you should make sure that you take everything away, and then there are 10 to the 24 atoms around them, that you have to take them all away and then keep only the ones that you need. Or you have to work at very low temperatures, or millikelvin temperatures, for some other implementations of quantum computers based on superconducting devices, and this makes that's very difficult in practice. In fact, you can see now that from the first prototype from our paper and the first prototype, then there was a time in which research was done basically in academic institutions, and then there was a steady, let's say, progress. In 2012, industry announced that they would to build a quantum computer. And 2019 came this experiment, which is called Google Supremacy Experiment, where they showed that for some specific problem, a quantum computer, this first generation, can solve it. And we enter what we call NISQ era. This is noisy intermediate state quantum computer. So here, what we have are prototypes of quantum computers that we are building with very few qubits, 50, maybe 100, maybe up to 1,000. They are not perfect, they are noisy. And therefore, the quantum computations or the promises of quantum computations cannot be fulfilled here. And the reason, again, is like if somebody would give you a pocket calculator, and this calculator would make mistakes, there are errors, it's not perfect. And then you say 7 times 5, and then you get 33. Wow, almost. So it's a little bit similar what happens with these quantum computers, that they have errors, and therefore you want to use them for where they will be useful, then they don't work on that. So the whole goal of many people right now is to find non-academic problems for which, even though these quantum computers have errors, still can perform better than classical computers. There is a lot of money now given by companies, by states, and so on that are trying to do that. And they are also trying to get rid of these errors, to scaling up these quantum computers. And there are people that claim that in 10 years, or maybe 15 years, or 20 years, then we will have these real quantum computers that will be able to fulfill the promises of quantum computers. So what I want to show with this diagram is how long it takes, let's say, from basic science, research, industry development, and maybe to come to the market. And there is still a big uncertainty on when this will happen. And I think that scientists that are attending this talk know this very, very well. In any case, now we have big industry devoted to quantum computing, mostly in the US. We have very few in Europe, and very few in Germany. And what we have in Germany is what Guillermo mentioned. So it was announced in June 2020 within this Konjunkturpaket of the German government to beat the economic effects of the pandemic that we have. We're promised 2 billion euros for 5 years for quantum computing. At the same time, the EU has a flagship on quantum computing, a flagship program of 1 billion also. And the Bavarian government, that's where I'm sitting, they just gave us, let's say, when I say us, let's say the scientists and the academia in the Bavarian area, 300 million to build what we call the mini quantum valley. And this, you say here, the Minister President, Mr. Söder, when he signed this contract, just creating that. So there are many expectations. There is a big hype on quantum computer. And from the scientific point of view, we make it clear that at the moment, what we have is a device that we don't know what is useful for. To know what's the use. It's like a laser when it was discovered. It's a solution for a problem that has to be found. So we believe that this is what happens with the first generations of quantum computers. And that's what we want to do research and to make them as good as possible. And hopefully, in the long run, there will be practical, let's say, scalable quantum computers, which will be useful for the society. And with that, I would like to finish thanking you. And so Guillermo also mentioned that an important part of my career is the group of people I'm surrounded. And that's a picture that we have. So typically we have one retreat all together. We go somewhere to the mountains, somewhere in Austria or in Bavaria, and we meet there for 3 or 4 days. We have talks and exchange, and this time we couldn't do that. So what we did is to have it online. Probably you're familiar with this gathering code. And what we had is, they're very original. So they invented it. So we had some Corona Olympics. So we make an Olympiad among the participants. And this was very freaky because, for example, I can tell you that one of the things that we had to do I was not participating. What they have to do for this Olympiad is to solving integrals. Okay, so this is how what they spend their time, just solving integrals. Anyway, I'm very happy with the people that I have, and actually, I've been extremely fortunate to be surrounded by such a clever people who are much cleverer than myself. I can promise you that most of them are very, very brilliant people. And so with that, yeah, I think that I'm finished, and I'm very happy to answer any question.
Thank you very, very much, Professor Cirac. Also, a note to our audience, this wasn't sent out with the materials, but before asking a question, you also have to solve an integral. It's being emailed to you right now. I have to say, I am really delighted with your laser analogy, because as you were describing it, I was Googling, like, this sounds like the problem, like the solution looking for a problem narrative of the laser, and then you immediately brought it up. But it helps me actually ask one of the first questions, because this particular subject of quantum computing has this hype. Every new technology has a hype, and the threat of a winter, I have to say, we're almost 10 years now from when graphene got the Nobel Prizes and the relevance, and we thought by now we would have graphene-based materials, and we have some, but it's taken longer than what we actually think. But this particular problem also has a component of state interest because of the expected capabilities that the first general purpose quantum computer, or not even general purpose, but let's say some cryptographic brute forcing algorithm could do. And this is also why countries are interested in being players. However, I don't think that you were thinking of this back in 1995, when you were in a room with 13 people talking about the future of lasers. So I would like to start by asking you, when did it become apparent that this kind of like runaway effect from simply making a proof of principle to the first experiments? I know that you have given us this very nice timeline, but when did you become aware of the weaponization of the quantum computer, just by its sheer power, computing power?
Okay, so my experience was at the beginning that I wanted to solve a challenge. It was, of course, I mean, there was an application behind, and I thought that was important. But at the moment, at the beginning, I was not thinking that it would have any impact or anything. There was a challenge, an intellectual challenge of how to do something that may have some impact, and I didn't know when this would happen. And if you look at recordings that I have already from the late 90s or 2000, I was always saying that I'm sure that there will be some applications of quantum computers. However, I think that they will take, 30 years or something like that. And I say 30 because probably at that time, people forgot about that I say that. Okay, so that was not clear when this will happen. However, this will take a long time. And so this is why, my career is not based on quantum computing. I have been working on many other things, because this is something that it was not my main topic of research for many years. But nevertheless, when things change is when industry got interested. So, and the reason for that is because in research, we have some funding, but so typically we are interested in developing, but more from the scientific point of view, driven by curiosity. So when my colleagues were building the first prototypes of quantum computer, they were not thinking about beating all the records and taking it to the market in the shortest time as possible. What they wanted to know is to investigate if there were no new phenomena in quantum physics. You have nobody was able to isolate these 20, 30 particles before and to see the laws of quantum physics in these particles. So they were interested to see whether there's something happening there that it's not knowing. However, when industry goes there, then they have a goal, and then they have money. And if they consider that this is interesting, they go ahead. So then, somehow we knew that this would advance much faster, and that's actually what happened. So I think that when I saw that people like Google and some other big companies were interested, is when things basically changed, and I thought that this was probably being accelerated.
So, using one of the notions that you just put forward, what is the role, or what is even the space of curiosity in the modern, highly professionalized academic research? Not the industry, but in the academic research. how much of a balance do you have to strike between actually giving freedom to, say, your postdocs or your PhDs, but also not too much freedom?
Well, this depends on the subject. And I think that there are some subjects which have to be very application oriented, even in research, and some of the subjects which are more blue sky research. And it's not that one is better than the other one. Both of them are needed. So it's always, so some of the people say, okay, so we need applied research because this is what this has impacted the society. And that's true, that's definitely true. And we need applied research. However, more basic research may have an impact or will have an impact in 20 and 30 years. So this is an investment that we do in the next generations. And actually there have been economists that have been looking at, so what is the effect of applied research in the long run and basic research in the long run? And they see that the basic research actually is very profitable. So what you invest, you get much more in the long run, not in the short run. And that's true. And I mean, you think of anything, internet or whatever. I mean, that's the vaccines that we have now. I mean, there's a lot of basic research that without that, it would not have been possible to have that. So my answer is always both are important. We have to do both at the same time, not forget any of them. And now, depending on which you do, then there is more space for curiosity-driven research or more applied.
So regarding this particular note, because we had some meetings preparing this, and I remember bringing it, you brought this point yourself up. Sorry, that was German. You yourself brought this point up, that your lab is not exactly in its internal structure and balance between PhDs and postdocs isn't really mimicking what the other experimental labs around you are doing. So could you perhaps tell us why you're doing that, or what your goal is in when doing that?
Yes. Okay. So when you get one position like a Max Planck director, this is my position at the moment, then in your contract there is a very generous funding. So this means that you have some funding, and then you have to employ it to do research, and then there are different strategies. Probably you're experimentalist and you have to build equipment and so on. I'm a theorist, so my equipment is basically computers, so it's not very expensive. So I have to decide how to organize the group. And then I decided to organize it in a kind of inverted pyramid. Now the numbers that you gave is a special situation. And because we have now, you mentioned that there are 3 PIs at the moment. There used to be 4 PIs until 1 month ago. But this is why there were more PhD students. So typically in the group, there were something like many postdocs and few PhD students. And the strategy that I had behind is that I wanted to give, to have many postdocs that would be independent postdocs. So these would be people who would come here and would do independent research, meaning that they don't have to collaborate with me and I don't tell them what to do. Now, in practice, I mean, some of them talk to me and then we decide and then we do things together, and some of them work with me closely and some of them don't work closely. And one of the things that I had in mind is that I would like to make a circle so that the people who come here gain independence. They were very selected, it was very selective. And then these people will probably be very successful. And if they are successful, then this will attract very good people to the group. And these people will also be successful. And so this makes a circle. And so that was the strategy that was behind everything else. And on top of that, then we also hire PhD students. But so typically we had something like 6, 8. So this was the number, because there are some projects that we wanted to develop and we wanted to carry out some things. And these were related to that, even though some of the PhD students work also directly with the postdocs. So it's one possible strategy. In some cases it works, in some cases it doesn't work. In my case, I think that it worked very well. So you lose the list of the previous postdocs in my group. I think that something like 65 or 70%, they have permanent academic positions. And so that's a very high out of, I don't know how many, there will be something like 50 or 40, something like that. So this was a very successful strategy. And this was the key behind. And that was what I was planning from the beginning.
So before I open the floor to the questions, which I'm seeing in the chat, I have a couple of quick follow-ups because I was looking at your numbers from the latest CV where you list the alumni of your group, which is about a list of 120 names. I just counted the times that the word professor or assistant professor pops up, and it's a total sum of out of 120, 50, which is like over the last 20 years, I guess, that since you've been listing alumni. So it's like 1 in 2 of the people that went through or by your lab got a permanent position, which is, I guess, I mean, I'm not going to moneyball this. I don't know about these metrics, but sounds pretty impressive. Just
yeah. So that it doesn't seem that there is a contradiction with what I said before. So of course, the PhD student take much longer in order to get the professorship. So you include the PhD. This is what the number is different. I was including only the
no. I didn't want to by any means correct you. I just
I understand.
I was looking. Yeah. Also, when I was going through these numbers, actually, I have a quick follow-ups. You, of the universities listed where these people went after going through your week, 40 out of the 120, 40 are in Germany, and 20 are in Spain, 12 are in Austria, and then it goes down UK, China, Switzerland, USA, France, and Denmark. So it's also, I would like to give relevance to the fact that you are pulling talent and putting it back from Spain. You are somewhat of a school maker of people that get formed in your lab and potentially belong to this circle that you talked about. And then somewhere there in the middle, you say that PhD students even sometimes get tutored by postdocs. I don't know if I understood you correctly. Does that mean that you are usually highly involved in guiding the PhD students through their thesis?
Most of them, yes, but there are some cases in which this is not the case, and in which, for example, I mean, you see the papers that are written in my group. Some of the PhD students have a paper where I'm not a co-author of that paper. And so what I have to make sure in that case is that, I don't just say, okay, you work with that and do whatever you want. And the reason is because I have to take a responsibility. At the end, I'm legally in Germany. I'm the only one who has authorized to be a supervisor in the thesis. So I have to make sure that the project that is given by the postdoc makes sense and will lead to something, because otherwise it could happen that the postdoc goes away. And so what happens with the PhD student? So this is why this happens, but it's under control. So it's organized in a way that nobody would all of a sudden discover that they cannot finish a PhD. Yeah.
Just before I open the round to questions, first the one in the chat, just a ballpark figure, how much % of your time is invested in managing such a ship, and how much is invested in thinking? Okay, so if you take, and let's exclude the last year, because it has been very special. If you exclude the last year, it would be, I think that 20% administration, 80% research. If you take the last year, it was the other way around. And the reason is because of this quantum computing thing. So this packet that the German government brought up actually kept me very busy, because they put me in the Expertenrat from the chancellor. And then I had many meetings. Then the Max Planck Society wanted me to be the representative in many places. And so I spent a year just having a meeting after each other. And this kept me extremely busy. And I'm hope really to go away of that very soon and come back to research, because I really hate this life. Mm-hmm. Okay, so that's that from me so far. It's moment to either ask the questions. We have a question from Vincenzo Florentini. I don't know if you, since I cannot see everybody here, I'm going to read it out loud, but if somebody feels they can unmute themselves and take over, please do so. Computing seems fairly primitive, but is there a quantum technology that is ripe for application, cryptography and communications perhaps? This is kind of answered a little bit. I don't know if I am understanding the spirit of the question again, because I'm reading it in real time.
Yes. So I think that it makes a lot of sense. So there are many quantum technologies, and quantum computing is one out of these many quantum technologies. So the idea of quantum technologies is to use these principles from quantum physics that I mentioned, superposition, entanglement, and so on, to do something better than without these laws, and to build better equipments. And then one application is computation, build better computers or faster computers or more powerful computers. There is another application in communication, so to build more secure communication or even more efficient communication. And that's what is related to quantum cryptography. And so there are applications in the field of quantum cryptography, and they are more advanced. So they are already commercially available. However, at the moment, from the economical point of view, they don't compete with the classical cryptographic methods. But it's it's a story that if you build a quantum computer, then it will be able to decrypt all the encryptions that we use nowadays. So in practice, so if today a country, let's say that is not in Europe, would have a quantum computer, then the security, not only of our governments, not only of the military, but also our security would be in danger. And the reason is because they will be able to decrypt all the messages, including when you buy something by Amazon or in eBay or whatever. All this information is encrypted and a quantum computer could decrypt it. And this, then a way around it, one possible way around it is to use quantum physics in order to build a cryptographic method that cannot be hacked even by quantum computers. And that's quantum cryptography. That's what is more advanced. However, since there is no quantum computer, then there is no need for quantum cryptography. And that's why it's still, let's say, it's not a success, commercial success. However, people think that even though you don't have a quantum computer, even if you don't have a quantum computer, but if there would be prospects that in 10 years there was a quantum computer, then what will happen is that the messages that you are sending right now would be decryptable in 10 years. And this could compromise not us, but maybe some big industry or government or so whatever. That's why there is a big push also from industry and especially from governments to grow in the field of cryptography, quantum cryptography. There is another technology, which is metrology. So quantum computing is also useful in metrology. And these, I think it's a very interesting applications. They are not developed all the way, but the idea is that if you use, again, these basic principles of quantum physics, you can make much better sensors, much better meaning more precise in some particular instances. So for example, you could measure magnetic fields with more precision than we have right now in small regions, nanoscopic regions. You can measure temperature. You can put one device inside a cell and then measure the temperature of the cell. So this will allow to do things which are difficult and that hopefully have applications in medical research as well. Or, I mean, there are people who are sending now, for example, gravitometers that are based on quantum technologies and that they are more precise than any gravitometer. So gravitometer measures somehow how the constant G changes. And so you know that we learned in school that this constant is 9.81 newtons, whatever. However, if you move it a little bit, it changes maybe in the 12th digit. Okay, and so you're able to measure how this G changes by moving a little bit. Then this depends on what is behind you, what is below you. For example, if there is oil, there is gas, there is carbon, it will be different how it changes. So it's a very good way of detecting. You have a lot of precision. And so this is the precision that quantum physics brings you, and there are applications related to that.
So the same, Vincenzo, this is like for a quick answer, because I guess this is like a feud between quantum computing architectures, superconducting or optical qubits. I mean, most of the pictures that you get are first on the Google computers, the ones that look like candelabra hanging from the ceiling. These are it's superconducting semiconductor. Perhaps I'm a bit out of my depth here, but it's not the design proposed by you. So perhaps a couple of sentences on that, and then we move on to the next question by Juan Miguel.
Yeah, so there are many technologies now that are trying to build quantum computers. There is a trap ion, there is superconducting qubit, there are semiconductors, there are color centers in diamond, there are photons, there are quantum dots, there are many. And it's not clear who will be the winner. That's a race in which things are moving like that. And so, for example, the most advanced right now are without any doubt trap ions and superconducting qubits. The superconducting qubits are very good because they can be easily scaled up with lithographic methods. However, they live in a solid, they're in a solid. So they have some environment and we want to isolate it. This is why
the errors are higher there, I guess.
The errors are more difficult to control. The ions are very nice because they can be isolated, so they're perfect. So the best clocks that exist now are based on trap ions. And however, they're difficult to scale because they have to be separated. And so each of them have their pros and cons. And so that's why there is not a definite technology where everybody is betting. So I would say that the big companies are typically taking superconducting qubits. Then there's like some other startup companies or even big companies like Honeywell are taking trap ions. And then there are some other companies like Microsoft who started making very exotic ideas that turn out not to work for the moment. Majorana fermions are called. And so that's why there are many options.
Also, a very quick one, because I know that we have people working in the patent office in the audience. Do you have any patent on your name regarding this architecture?
Okay, so I don't have any patent, and I can tell you that I have. Okay, so then at some point, I mean, I've been working in different technologies. So I mean, we for example, develop what is the concept which is called quantum repeater or quantum communication. And this we wanted to patent, but then the company bought us the patent. And so since at the time, this was 2001, we learned that the patent expires after 25 years. And then we were not, we're thinking that there would be no commercial possibility in 25 years. This is why we sell the patents. So we got some money for that. And now they're 20 years, they still have 5 years left in this company.
So this is the time unit of the comic that I was telling that people usually ascribe to theoretical physicists.
I see. And then I have another one. I have another one on some protocol for, it's basically quantum credit cards.
Interesting. Okay. Next question by Jose Luis Toca Herrera. What about solving the structure of macromolecules, chemical bonding, and the interactions between molecules?
Okay, so now it comes to what is a quantum computer useful for? And if we had a quantum computer like this scalable quantum computer, then I can tell you that we know that we could have very important applications in chemistry and quantum chemistry, what is called quantum chemistry, and that's a very clear reason why. And now the big question is whether these first prototypes of computers that are noisy and so on, whether they will have applications in chemistry. And that's one of the, let's say, more likely places where they can have applications. However, it's not clear yet. So you will hear many claims. You will see that BASF and many other companies are putting a lot of effort in trying to use these existing quantum computers for chemistry, but there is no evidence so far that there will be any advantage.
So Pablo Lanillos, I didn't see your question in the chat because you didn't put it. So I was looking for sentences that look like questions. Pablo, feel free to unmute yourself and ask it.
Yeah, no, first of all, I want to thank Ignacio for the nice talk and this event. Actually, I think is really cool. I have a question regarding also technologies that like the previous one. I know by heart that there is some theoretical machine learning experts, really big guys in the world of machine learning in Amsterdam, that they are starting this approach of quantum machine learning in relation with Qualcomm, for instance. And I was seeing, I mean, I'm not an expert in quantum computing, but I'm seeing that this kind of noisy quantum computers and all our techniques that we are using right now, they also have these kind of errors because we use probabilistic approaches for classification and so on. So what do you think about this new trend that they are trying to push that is related to machine learning, computer vision, and so on? Thanks.
Okay, that's one of the other places where there might be some applications. However, again, I have to say that at the moment, as far as I know, there is no evidence. However, there are some funded reasons to believe that this may be the case, even with these noisy devices. So as you know very well, at the end with machine learning, what you want to do is to parameterize a function, a probability typical distribution in terms of some parameter, and then optimize the parameters such that the probability has some figure of merit. So at the end, it's a question of how to express probability that exists in nature. And the second is how to be able to optimize in such a way that you get something that corresponds to what you want to describe. Now, quantum computer can help you in the first place because in this quantum physics, whenever you do something with a quantum computer and you measure, then you are sampling according to some probability distribution. And some of these probability distributions are very hard to sample with classical computers. In fact, this Google supremacy experiment was exactly about that. What they showed is that there is a probability distribution that you can sample with a quantum computer and that you cannot efficiently sample with a classical computer. So the hope is to say now, okay, let's take what Google did. Let's put some parameters and let's now consider the probability distributions depending on these parameters. And let's try to see if with that we can express some probability distributions that we are not able to do with classical computers. That's the hope and that's the idea, which is good. The question is that there is a second step, that is, how do you optimize this? Well, first of all, it should correspond to the one. So you have, this probability should correspond to one that has some relevance. But second, you have to be able to optimize it. And the machine learning, that's, very clever ways of doing that. And with quantum computers, some of these ways don't work that well. It's not clear that they will work so well.
Thank you. Thank you very much, Pablo. Pablo is my predecessor as a VP of CERFA. He's now a full professor in the Netherlands. So I guess
I'm not full. Still not, but okay. Thank you.
Okay. So Juan Manuel is talking about Moore's law, which perhaps you can explain for the audience. Is coming to an end with quantum computing. But I think I'm going to read the question out loud. Moore's law is coming to an end. The next step is quantum computing. But which component equivalent to the CMOS transistor in classical computing will be used in quantum computer? The trapped ion? I think he's not asking the trapped ion versus the other architecture, but what is the limiting step in the quantum Moore law equivalent? I hope I didn't butcher that, Juan Miguel.
Okay, that's a good question. So maybe like to give a little bit of background to the audience. And so you know that the first classical computers were developed in the 40s, and they were occupying huge buildings because they were made out of bulbs. And then at that time, there are very famous statements by the president of IBM, for example, for Watson, and saying that he could not believe that such a computer could be used by more than 5 people in the world. They're really written statements because, of course, it was occupying the whole building. Now, the breakthrough happened when transistors were discovered. And once they were discovered, then it was possible to miniaturize them. So to then make them smaller and smaller and smaller. And by making it smaller, then 2 things happen. First of all, is that you can increase the memory because you can put more data in a smaller volume or the same volume. And the second, which is more important, is that computer, the time why the computer takes time is because electrons, which are the ones, the physical particles that carry the information, have to move from one place to the other one. And of course, if you have something that is smaller, they have to move less distance, and therefore they are faster. So this automatically also accelerates the computer. And now, since the transistors are being very smaller and smaller and smaller steadily, then this means that the computer have also growing steadily. And actually there is an exponential law, and this law is the Moore's law, that every 18th month, the speed of the computers, or the density of information that you can store them doubles. And so now we are in a similar situation with quantum computers. We have like the first generations of quantum computers that are this big apparatus that you have. Nobody could think that you could build a quantum computer based on, for example, the superconducting qubits. You need a dilution refrigerator that occupies something like half a meter by half a meter, something like that. And this is for 53 qubits. Now, for a real quantum computer, you would need of the order of millions of qubits to be competitive. And so this automatically means that you will have to have a dilution refrigerator, which is of the size of a building. So we are in a very similar situation, that nobody can believe that this could lead to anything. And this is why there is one hope, and this is more a hope than anything else, is that there would be a discovery similar to the transistor. So there would be somebody who would figure out a way of shortcutting, and that's the equivalent. And that the question was about that. So where is it? Well, if I knew that, then I would do that myself. So this has not been discovered. And that's why people are taking traditional approach. Yes, okay, let's try to do engineering and try to grow in the way that we know, but let's try some other technologies, because in one of these new technologies, when people may discover this equivalent to the transistor.
This is another question by Juan Miguel, the author of the question that I just asked, that I'm going to spin around a little bit, because they say that he uses the term general purpose, which I think is an issue that we should touch on, so that I guess when we talk about quantum computer, we're not really speaking about a computer like the ones that we have on our desktops that is just somehow quantum. Let's air quote that in whatever that means. currently, even the most advanced quantum computers that we can envision are what are called special purpose machines, which is their function. They are not programmable as programmable as normal computers are right now. So that's like another barrier to making them as widely applicable as the rest of the computers with current architectures. So I would like to hear your thoughts about this analogy that sometimes people make with graphical processing units, which are now the backbone of machine learning algorithms that we were talking about before were developed for something completely different. And they were kind of a special feature machine. They were just designed to accelerate the computation of applying textures on three-dimensional objects for video games. And now I would say 1/3 of machine learning is unthinkable without them. So what are your thoughts on this?
Okay, so a couple of thoughts. So the first thought is that somebody asked, so will we have a quantum computer on our desk in 20, 30 years? And I mean, I cannot imagine something like that because I mean, in my desk, at least at home, what I want to do is to answer emails and write some text. I do some computations, but this is because I'm a physicist. Typically people don't do these computations, they do the tax declaration and things like that. And so I think that this will not, I mean, a quantum computer doesn't give any advantage for the things, for this kind of things. So this will give a practical advantage for difficult computations like the ones that are done in supercomputers. So this is why one has to think that quantum computers would complement supercomputers, not the desktops. Although, I mean, one never knows. I mean, if you look back, so people could not imagine that internet would have the applications that we have now, that we'll have cell phones or things like that. So you never know. But in principle, I think that it was more to replace supercomputers. Now, what you were asking is the supercomputers are general purpose, many of them. So you can go there and to solve a problem in climate or in the forecast, weather forecast or something else. And there are some other ones which are like a special purpose. And like the ones that you mentioned, and so something similar is already happening with quantum computers. So there, if you talk to IBM, they will sell you now you can buy a quantum computer. You have to pay something like $10 million or euros. You will buy one, and it is a general purpose quantum computer. They will give you the software, they will give you the operating system, and you will be able to program it. The only thing is that you will have 20, 30 qubits. And whatever you can do with that, you can do it also with your laptop, because I mean that's not enough to gain with respect to your laptop, but they exist and you can program there. Some people like AWS are offering quantum computing on the cloud, and so you can just program whatever you want there with different software. They're as I'm mentioning, operating systems and so on. And there are some people who are having that. Some of them offering, some of them are just charging you for using and so on. So this exists. However, I have to say that this is not so promising. And the reason is because we don't know applications of these quantum computers. So the problem is that even if they build something with 1,000 qubits, then it will have errors. And whenever you want to solve a problem, you will get the wrong result. And not, I mean, that's not what you want with a computer. There are some problems for which we already know that there are applications. These are related to, not to chemistry, but almost to what we call quantum simulation, to solving problems in material science and so on. And for that, one of the specialized quantum computers that solve these particular problems, and then they use this fact in order to be much more powerful than the quantum computers that are used for that purpose. And so this exists, and in fact, they are being developed and in many places around the world.
I think this is the spirit of the last two questions that popped up in the chat. We've already answered whether citizens will have a quantum computer at home with different degrees of trust in how the future would look like. So I think somebody called Alan, he says, after quantum computers, is it possible to expect another basic quantum physics discovery that would lead to another groundbreaking development in the next 5 to 10 years, which is use the quantum computers for discovery about physics themselves, which I guess is a hard question to answer. And
yes, but it's a very interesting one. And in fact, there's some people who are thinking about that. Let me just give you an example. So imagine that you have a quantum computer and you build it. And just by building even these noisy quantum computers, we are crossing a frontier that we never crossed before. Okay, so we will be able to have many of these small particles in a controlled quantum state, what is fulfilling the laws of quantum physics without an environment. Typically, we have environment and we know that this kills most of these properties, but we will have something. And so the first thing that can happen, that you can build a quantum computer. The second thing that can happen is you see that quantum physics is wrong. And so there are some corrections to quantum physics. And so if there are corrections of quantum physics, then you can just say, oh, that's very bad. Or you can say, oh, that's very good, because this, every time that we find that something is wrong, this gives us new opportunities. And in fact, so if you talk to some people in high energy physics, they will tell you that one of the unsolved problems in physics, as you probably know, is the unification between quantum physics and general relativity. And there are now new ideas of how to address some of these problems. And it's believed, so basically it is related to black holes and information. So what happens when information comes to black holes and when the black hole evaporates, how this goes out and so on. And then they say that quantum computers can help us to reach, not black holes, but to reach the solution of some equations that we will never be able to solve with classical computers. This will tell us something about violations of quantum physics due to gravity. And if it's like that, this could open up new possibilities. I give you one. There is a famous physicist called Scott Aronson, who has a very famous blog, and it's really famous in the quantum field. And so, for example, he had a paper in which he showed that if it was possible to have closed time curves, which basically means traveling to the past, then it would be possible to solve problems that not even a quantum computer can ever solve. So all the problems that could be solved right away. And you could say, well, I mean, going to the past has kind of causal problem because you can kill your grandfather before your father was born, so how comes? And then you go to philosophical contradictions. However, there is this kind of also quantum physical idea that you have this many world interpretation, and then what you could go is to a different world back in such a way that there are no contradictions. So there are people who write even about these things. And so that's a completely speculative. I don't think that there is anything right in that, but you see that, I mean, it opens up new possibilities. And now if I put the cap of a scientist, I'm very excited about exploring these possibilities more than building a quantum computer and to, I mean, let it run and to solve some other problems.
So to summarize a little bit that last answer, so you think that either the quantum computer helps us because in the process of creating the quantum computers, we are arranging matter in an arrangement and to an entanglement degree that we never have seen before, and then we might expect to see something that helps us correct quantum physics, or quantum physics stays the way it is, but through the computational power of the quantum computer, we solve equations that enlighten us about situations in black holes and other esoteric places that would themselves be enlightening.
Right, but I think that this is not an or, is an and. So I think.
Sorry, yeah,
meaning that even if quantum physics is not correct, it has to be only to a very small extent. And it turns out the quantum computers are very robust in some sense with respect to perturbations of quantum physics. And so still, if quantum physics was not right, quantum computer would have an advantage, but this would open up the possibility of other laws of physics.
Mm-hmm. I think this is going to be I don't see any more questions. No, there's actually two more questions. So Pablo Gonzalez wants us to know a little bit more about the actual status of development of quantum computing simulators today. I don't think, Pablo, has this been covered a little bit by the answers so far? I don't exactly understand what you mean. So if you want to unmute yourself and ask the question, feel free.
Yes, hello. But I was writing the question just when he was speaking about simulators. But nevertheless, I would like to know a little bit more, because surely, especially for programming, I saw some questions about high-level computer languages and so on. And surely, simulators now at this stage would anticipate many problems that we have in the future. I take the opportunity to make another question. At the beginning, well, first of all, congratulations for your success. And at the beginning, the first time I heard about quantum computing, I really was thinking about the previous phase to the normal computer, to quantum computer, should be a state in which we can code and calculate not in binary code, so in codes of 3. So find a state in which a particle, an electron, or we don't know because we don't know how to do it, to go with a state 0, 1, and 2, and go to the other one without passing for the previous one. Do you know something about the development of this kind of future computers as well? Thanks for the answer.
Okay, thank you. So about quantum simulation, so I would say that, I mean, that's probably the closest in time application of quantum computers to simulate some problems that cannot be, or some models that cannot be simulated with classical computers. And that's in particular problems that are called of some particular kind. These are called Hubbard models and so on. They have some names. And these are problems that appear in material science. And so there is a big effort internationally in order to build these quantum simulators. These are dedicated computers to solve these particular models, because we know for these particular models, we know very well that there are many limitations with supercomputers, whereas even with this first generations of quantum computers, they already predictions that they will be able to solve these problems. In particular, in our group and here in Munich, we have a big program on solving and building and showing how to, I mean, the software, to write the software for these quantum simulators. That was question number one. The second question is about instead of using base 2 kind of computation to do base 3. And so, I mean, that's very different from quantum computation. And the reason is because it doesn't change the complexity. So if you have 3 levels instead of 2, or 3 states instead of 2, then you will get a factor. I mean, you're able to do that. At most, you will get a factor in your computation. So you'll get a factor of 2 or 3 or 4, but you will not get a factor. You will not gain a factor that would change your complexity class. Meaning that the problem, if it takes, I mean, I'm using now some kind of jargon, if it takes an exponential time or is in a class that is called NP, is NP complete, any NP hard, with binary code, it will be with trinary code and with any code. So this means that there might be some specifics where you gain a little bit, but this will be a little bit. So quantum computer, what it does is that it changes complexity class. Problems that are in NP, all of a sudden are not in NP, are in BQP, which is the class of problems that the quantum computer can solve efficiently. So that's a main difference. So you can have some gain with writing with some other codes. However, this will be just a factor in front of your time, which will be very useful, but quantum computers doesn't deal with factors, deals with the scalings.
So I think I read in Juan Manuel's face that we should be coming to an end, perhaps. I wouldn't want anybody to have the feeling that the questions couldn't be answered, but I really have to wrap up as per request. I would like to just propose or give a statement to you and pick your thoughts, and then Professor Cirac, you feel free to close the event yourself. This event is about you. It also ties nicely with the last question, because you were mentioning things that go into complexity theory or information theory, NP and PQ, and all of these things. So I have read a statement in preparing for this session that quantum computing is the place where physics and information theory come the closest in all of physics. Would you agree with this statement, and what does this statement suggest to you? And perhaps take it from there and feel free to, I don't know, Juan Manuel, do you want to say something before closing, or can we give the floor to Professor Cirac?
I have one question myself, but I can ask it later. And I don't know, just as a suggestion, I don't know if there are other participants who have questions beyond the realm of quantum computing, and you may be interested in asking. I don't know, but I find this discussion super interesting, and I'm sorry, Professor Cirac, we are abusing of your patience and making you speak a lot, but I find this really fascinating. But yeah.
Well, yeah, just because the intention of these dialogues is to also have some subjects that go beyond the realm of the scientific matter at hand, actually Professor Cirac was kind enough as to present a more personal view of his trajectory. And here we are talking about binary codes and complexity. So perhaps it's a very good tip that we should pivot perhaps towards more, I guess the Spanish word would be transversal themes that affect practitioners of science across all disciplines. I don't really know what to do with that pivot other than open the floor to these types of questions. If somebody wants to ask something more of a science management, I was trying to go into that direction before, but if not, there isn't really any other reason not to finish here. Again, I give the word to you, Professor Cirac. Quantum computing, I found the statement itself really beautiful. I am not a physicist, but I think that statement must be very powerful in its suggestion to you. So it's where physics and information come the closest.
Well, yes, and indeed. So, I mean, when we write a proposal for the EU call or somewhere, so typically we will start saying that in the last century, there were two scientific revolutions that became very important. One of them is the discovery of quantum physics. The other one is information science. And so the field in which we work just unites both of them and uses quantum physics in order to process and transmit information in new ways, and that were not advanced by people like Shannon, who were the inventors of information theory. So indeed, that's a way in which you can understand that now information can be treated with quantum physics, and it's physics also in the sense that the intuition and many of the new ideas that came in order to deal with the information are coming to physics. And yeah, so I agree with what you say. Yeah.
I've just been made aware that there's another question that's not necessarily about quantum computing, but more related to this intra-history. So Yvonne says that around the time that you were in Boulder, probably commuting with the University of Castilla-La Mancha, was when the first Bose-Einstein condensate came to be. So were you around there? What are your thoughts or memories of that time? I hope I captured the spirit of the question, Ivan.
You see, I was extremely lucky. I mean, I mentioned at the beginning that I was very lucky to be in the right place in the right moment. So when I was a postdoc, I was in Boulder, Chile, at Joint Institute for Laboratory Astrophysics. And so I was talking to Dave Wineland, who was awarded the Nobel Prize some time ago. And I was talking to the people who got the award for Bose-Einstein condensation. So in fact, I mean, had colloquies with them, with Erin Cornell and Carl Wyman. And I can tell you just one anecdote that happened at that time. So when we arrived there, everybody was trying to build, or there were many people trying to build a Bose-Einstein condensation. So one of the reasons, because it was predicted by Einstein in the 20s, and so there was a new state of matter, and it was supposed to be very important, but especially because somebody wrote in Physics Today that whoever gets a first Bose-Einstein condensate would get a Nobel Prize. And then this dragged many people to try to build this Bose-Einstein condensate. And then when I was there, so I'm a theoretician, there were several papers that appeared in 1993 that wrote that building a Bose-Einstein condensation in the lab was impossible. Okay, fundamentally impossible. There were 3 papers written just disproving the possibility. And we had a conference in Boulder, and then there were the presentation of these 3 papers. And I mean, there was 2 of them were Russian, another one was from somewhere else. And then at the end, I was very young, and so I was surprised. I was talking to Erik Cornell, who was the one who was building the Bose-Einstein condensation, and I asked him, but why do you continue trying to build it? I mean, now these very important guys told you that this is impossible, and then he told me, well, I didn't understand them. So he continued and he got it and he did it. And of course, it was theoretical computation, I mean, very theoretical, that assumed that you have to have an infinite system and blah, blah, blah. And then at the end, it didn't apply. And so this taught me a lesson that is that when somebody goes and says that something is impossible, is a good reason to try it.
Oh, so I am sorry, but the discussion has become very lively and we can keep going for some minutes more. So my friend Pablo Lanillos is asking a question. I think we're going to ask 2 questions about the same statement, because you have mentioned already twice that you were at the right place at the right time. Now, all of us, many of us are Spanish. We're in Germany. We've changed places. perhaps trying to be for a long time at the right place, so that at some moment we find ourselves in that happy coincidence. So I guess the question is manifold, but it's just like a way of switching gears, which is, can you even plan or try to plan to be in the right place at the right time, or do you just have to, it's the perspiration versus inspiration question, I guess. And the place that we all come from, or many of us come from, or many of us have tied to, is Spain. What are your thoughts about, the current politics, not without really going into the nitty-gritty of it, but certainly Germany and Spain are different places. We can all agree on that. And there has to be a reason why we are all here now speaking in English in Germany about the trajectory of a Spanish scientist. So first of all, where do we sign up to talk to Nobel Prize winners so that perhaps we get a chance? And second of all, what are your thoughts on the Spain versus Germany in very, very general strokes?
Okay, so my experience is that, of course, in order to be able to get an academic position and to continue and to have funding and things like that, there are different conditions. And so condition is to be, like you say, in the right moment, in the right place, also to work hard, also to have some, talent for what you do. Another word, this is more important, is to have passion for what you do, so that you don't go to the work and at 5:30 you start just looking at your watch every minute, and then even just making like that to see if it works, because you want to run away. And then there is another one, which I think that I have seen, like in many people in my group that later on have had positions, is that they somehow have been are recognized, let's say, in some circle, as some people that are associated to something. So there is, the people who got positions is because one of them is associated to, levitating particles in the quantum physics. Another one is related to tensor networks, which we develop here. Another one is developed. So they have some part whenever somebody, let's say, in the world is thinking about some particular topic, they will think about this person, maybe among 2 or 3. And this has been very important. So to find a niche where, at least in that niche, you have devoted your time, it, you're a specialist, and people consider you to be a specialist.
So this is what the German word usually called like profilieren. You have to create a recognizable profile that people associate you in one line to something.
Exactly. Something like that. Of course, this will require also, apart from hard work, maybe luck and so on, and then also that your boss has to allow you to have that and so on. So it depends on many things. So it's something that you cannot choose yourself, because that's clear. But that's, I think that has been very important. That's the advice that I give to the postdocs that come here. One of the first things that I tell them is, so always think, why are you working? What are you working on? So ask yourself, why are you doing that? Okay, that's the question. So why the taxpayers are paying me for doing that? Really like that. And try to find a good answer that convinces you yourself. That's very important. And the second is just find something which is ambitious, work on that, and become somehow an expert. That you don't have to be the #1 in the world, but just an expert on that. And then this will ensure that you could continue your career. That was my advice. Now, regarding Spain, you know this very well, has a terrible situation. The last 10 years has been really bad for young scientists. They didn't have openings. They have accumulation of many people. There are many people waiting abroad or in Spain for positions. They are not coming and so on. So the situation is really very bad. And I think that, many people say the same thing, and we have been saying that for many years, that, what we require in Spain is something like what happened in Germany, on Pacto de Estado, some agreement between all the parties, that's a national importance to have science and technology and education. And these are 3 things that are very obvious, that are important in a country. And they cannot depend on one government, one situation, one crisis or the other crisis, because this balances. And then whatever you gain in 20 years, so as I mentioned, I was one of the lucky people in the 80s, 90s, 2000. And then all of a sudden, what you gain, you lose it. With all the knowledge, all the money that you have put, all the things are lost. You guys go out abroad. Some other people come back to Spain, leave science, go to some other. So that's a very bad investment. And this requires really an agreement that goes beyond politics. And this is what happened in Germany. You probably know very well. There is this Pax für Forschung und whatever. And so they, I mean, in the time, I always say it in Spain, where, I mean, in any time that I have the opportunity to talk to a politician, whoever he or she is, or to the radio, to the media, whoever, I tell the same thing. Okay, in Germany, there was a crisis. I mean, you were not there, but in 2002, 2003, 2004, there was a crisis. And then they saw that the crisis was coming. And then the decision was, in the crisis, of course, they have to limit the budget in many areas. And however, they decided for science and education, they will increase 3% per year. After 5 years, this was a pact for 5 years, an agreement for 5 years. Then the crisis was even worse. And then they decided to prolong it. And then it was 2012, I think. And then in 2012 was when Europe was very bad. And then they decided to increase to 5% per year, not to decrease it. Okay, they decreased everything else, but this was a message, and a clear message. Like we noticed in our research, in our institute, that this was going up. And you see that Spain, and not only Spain, some other countries, it was completely the opposite. So whenever there was a crisis, one of the first things that was easy to just get down was the science, and that's and it's not only science. I mean, it has to be science, it has to be education, which is very important, and it has to be also innovation, industrial, and things like that, which drive a country. And this was not the case. So I think that this is a problem, a very important problem. There are many other problems in Spain as compared to countries like north of Europe, but I think that that's an important, that not only politicians, but also society, because we need society also to support. I mean, you cannot ask the politicians, do that against the society. No, you have to have the society behind. In Germany, they are behind that. You walk on the street and you'll see a number of scientists on all over the streets. Okay, so the society pay a lot of attention to science. And so that's what an exercise that we have to do, and we try to do, to convince the society and to convince the politician in such a way that they notice that that's something very, very important for the fate of our country.
So to close the loop back, and I think we really have to be closing it back, because you said that you dreaded this last year where you were put into the Expertenrat for this package. I see that you are on the board of many Spanish institutions and foundations and stuff like that. So I have to tell you that please continue to try to influence and lobby for, keep answering phones if they still call you, because we scientists, for us, you remain a very relevant figure, but whatever influence that you have, please use it. CERFA also tries to influence somehow policymaking through other channels in restructuring the scientific career. We have Elisa here, who's part of the task force, where, as I said before, we're not doing only events, but that is to say, just thank you for all the scientific work. Thank you for all the outreach. Professor Cirac, as I mentioned before, has an impressive record of outreach talks. And that's it from me, folks. I guess see you all the next time that we do these Science in Dialogue events. Our very own Pablo Lanillos will be moderating. We still don't know exactly when. This is why I'm not giving a date, because I don't want to be backtracking later. And thank you all for coming. I had a lot of fun, and I hope you did as well. Juan Manuel, I really am just going to give the floor to you, and I'm going to mute myself to make sure that I don't get going. And if I don't unmute myself, Ignacio, feel free to just say goodbye, and then we'll log out.
Yeah, just want to say thank you. Thank you very much, Professor Cirac. Thank you very much, Guillermo. This was a fascinating discussion. But I think the last word goes to you, Professor Cirac, and thank you all for participating.
Well, I can repeat what I said at the beginning. Thank you very much to the embassy for the support that is giving to CERFA, and I really hope that this continues and increases if possible. And second, thanks to CERFA, with whom I have been in contact in the past, and I hope to continue this contact, because I think that it's can be very productive for both of us. For me to learn how the Spanish scientists are doing here, and to try to help within my possibilities. And for CERFA to have some connection maybe to some people who can give you some advice. Thank you.